In section 5.2, we're finding definite integrals by the limit definition, which is theorem 4. Example 3 says find the integral from 0 to 2 of x cubed plus 1 by definition, theorem 4, and this uses the limit of the Riemann sum. Okay, and so you need to memorize what is the nuts and bolts of theorem 4. So what that is we have the integral from a to b of f of x, and that's equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. And that's not all, where delta x is equal to b minus a over n, and x sub I is equal to a plus I delta x. So lots of things there. The place to start is to notice what your a and b are. So your a is 0 and your b is 2. And so I'm getting that from what are called the limits of integration. The little number on the bottom is usually the number that's the least, and then the higher, the number that's up top is your b. So you need those to figure out your delta x. So we have 2 minus 0 over n. N is going to stay a variable. Now that we found delta x, we can find x sub I. That's our a, which is 0 in this case. And then we have our I delta x. So I times 2 over n. Okay, so from here, we plug in. So now the integral from 0 to 2 of x cubed plus 1, and the dx is sort of like the end, the bookends here. This is a package deal, the function in between. Then we go and plug stuff in. So we have a limit as n goes to infinity, and we have the Riemann sum. F of x sub I means that we're plugging in 2i over n for x, so we'll do that in the next step. Delta x is equal to 2 over n. And be careful here, that's times the function evaluated 2i over n overall. So let's go ahead and plug in now that function. Our function is x cubed plus 1, so we're going to put in 2i over n cubed plus 1. That's f of x sub I, or f of 2i over n, and then we multiply that by 2 over n. So now from here, you're wanting to do some algebra and simplify so that you can get the sum of either a constant, the sum of I squared, or the sum of I cubed isolated. Then we have some properties that we can use, or rules, to get rid of the sum of those things. So there's different ways to do this, but definitely since we're trying to get I cubed, in this case by itself, we need to get rid of the 2 and the n nestled up in those parentheses. Personally, I like to distribute the delta x part, which is 2 over n. But there is some variations in the algebra here you can do, as just a heads up. So the first thing I'm doing here is I'm going to write 2i over n. I'm going to use an exponent property that allows me to bring in the 3. So I'm going to have 2 to the third times I cubed over n cubed. That's plus 1. Oh wait, I forgot I'm distributing this step too. Times 2 over n plus, and then 2 over n, the second term. So I have some simplifying to do in that first term. I'm going to go ahead and do that. Also, I'm going to bring the sum in to each of these terms separately. So then what I have is 2 to the third times 2, so I'm going to have 2 to the fourth, which is 16, I cubed over n to the fourth, plus the sum from I equals 1 to n of 2 over n. So now I should start to be able to see what I have with regards to the sum of a constant, sum of a constant times I squared, or I cubed. So usually there's a constant part in here. With the first term you have 16 over n to the fourth, which does not depend on the sum. And so I can pull it out of that sum, and I'm going to do that. So 16 over n to the fourth, the sum of I cubed, plus, and then the second sum, what I have is just a constant. In other words, there's no I in there, and that's what the sum depends on. So you are given the rule for I cubed, the sum of I cubed. You don't need to memorize it, I would give that to you. And so that's n times quantity n plus 1 over 2, all that squared. And then the sum of a constant is nc, which is you need to memorize. And so in this case, what we're going to have, I guess I'll look more clear, that's a sum, is we're going to have 2n times n, because the constant is 2 over n. So writing that out, the limit as n goes to infinity of 16 over n to the fourth times, now big brackets on top, n times parentheses n plus 1, all that over 2, finish the brackets, squared, plus 2n times n. So at this stage we've gotten rid of the sum and all the i's, and so that's good. That's where we wanted to get at this stage. Now we're going to start working on evaluating that limit. And so usually there's a lot of simplification you should do first, because right now we get the indeterminate form infinity over infinity. And so doing that, I noticed a few things, like I need to bring in my square. 16 halves is 8. I can do that. So I have 8n squared times the quantity n plus 1 squared. Oops, I did something bad here. Backtrack. It's actually 2 squared in the denominator. So you need to use the exponent properties to bring in the squared. So 16 divided by 4 is 4. Then I have n squared, the quantity n plus 1 squared, and then this is over n to the fourth. So I can cancel a pair of n squares. Oops, 2 over n times n just simplifies to 2. So next stage, let's see what I have here. I think I'm just going to go ahead and use L'Hopital's rule, or do algebra. What should I do here? Doesn't really matter. I think I'll L'Hopital it. So then what I'll have is 4 times the derivative of n plus 1 squared. So I'm going to use a chain rule here, bring down the 2, inside stuff is n plus 1, new exponent is 1, derivative of the inside n plus 1 is 1. So that's it there. Derivative of the bottom is going to just be 2n. So trying to evaluate this again, I'm going to get infinity over infinity. So I could use L'Hopital's rule, but the algebra is kind of easy here, so I guess I'm just going to do that. Lots of possibilities here. We have 4, the equivalent, if I cancel the 2's, of 4n over n plus 4 over n. So just using the n in the denominator now as a common denominator, n's cancel. So what I have for where n goes to 0 as n goes to infinity, so all that I have now is 4 plus 2 when I take that limit. So the result is 6. So that's the answer, and we can move on. I just want to quickly show you the graph of this just so you can get a visual. But the definite integral can be interpreted as area between the curve and the x-axis, where we have positive area above when the curve is above the x-axis and negative below. You have both the curve dropping below and above the x-axis for an integral you're doing. Then we interpret the overall area as the net area. So it would be the sum of the positive and the negative area. So here we have a simple case where we just have from 0 to 2 the curve being positive between 0 and 2. So the area under this curve dropping down to the x-axis is exactly 6, is what our answer means.